Example 3, still in 11.3. They want a Maclaurin series for e to the x and its interval of convergence, and then they want another step. Okay, so part A is to find the series. So, same as always, it's Maclaurin, so it's centered at 0, so we plug in 0, we get 1. This is an interesting series because the derivative of e to the x is e to the x, centered at 0, still 1. I don't think I need to do very many more, that you realize each and every derivative is going to be 1. So my series is going to be 1 plus 1x over 1 factorial plus 1x squared over 2 factorial. Notice I don't have any x minus anything because it's centered at 0. X cubed over 3 factorial, and so on, out to the x sub n over n factorial, which the summation turns into k equals 0 to infinity, x to the k over k factorial. That was a nice easy one. So that's part A, is to get the polynomial. Part B is to find the interval of convergence, and so I would use the ratio test on this. The limit, as k goes to infinity, I'm going to have x to the k plus 1 over k plus 1 factorial times, flip it over, x to the k is going to cancel and leave 1x. K plus 1 factorial is k plus 1 times k factorial, so the k factorial cancels. So I'm left with the limit as k goes to infinity of 1 over k plus 1 absolute value of x. As k goes to infinity, 1 over a huge number turns into 0, so I get 0. 0 is always less than 1, so this is going to work everywhere. The radius is infinity, the interval is negative infinity to positive infinity. So that's part B. Part C says, use the Maclaurin series for e to the x, the part we did in part A, to find the Maclaurin series for x to the fourth e to the x, oh my goodness, x to the negative 2, e to the negative 2x, and then e to the negative x squared. Okay, first one. All I have to do is multiply the original polynomial, which was e to the x, by x to the fourth. So I'm taking the original, x to the k over k factorial, and multiplying by an x to the fourth, which means I'm going to get the summation of x to the k plus 4 over k factorial. Writing out a few terms because they want me to. If I stick in 0, I get x to the fourth. If I stick in 1, I get x to the fifth over 1 factorial, x to the sixth over 2 factorial, dot, dot, dot. Okay, so now if I want to do e to the negative 2x, and I have e to the x, I'm trying to get e to the negative 2x, all I need to do is replace every x in my polynomial with the negative 2x. So my polynomial, the summation is going to be k equals 0 to infinity. Every x gets replaced with a negative 2x. So there it is. And if I wanted to write out terms, I probably would want to separate this out because we like our negative sign to be separate from the rest. So I would make that a negative 1 to the k and then a 2x to the k over k factorial. That way I would see the alternating. Sticking in 0, I get 1. Then I get a negative. Sticking in 1, I get 2. Sticking in 2, I get 2x squared. Then I get a negative. Sticking in 3, I get 4/3 x cubed, dot, dot, dot. And then the last one, same idea. We want to go to an e to the negative x squared, so I'm going to replace every x with a negative x squared. So the original summation, instead of being x to the k, it's going to be negative x squared to the k over k factorial. Again, split off the negative 1 to the k, And then we have the x squared to the k, which would be x to the 2k over your k factorial. And if we listed terms there, we'd get 1. And you can do it either way. You can stick in 0, stick in 1, stick in 2, or just go up to the original function and replace all the x's with negative x squares. So then you get a negative x squared, and then you get a positive x to the 4th over 2 factorial, and then a negative x to the 6th over 3 factorial plus dot, dot, dot. All right, that finishes example 3. Oh, one more note about this. Because the original series worked from negative infinity to infinity, by substituting things in, it does not change the radius of convergence or the interval of convergence. So every one of these still has an interval of convergence of negative infinity to infinity. And you could prove each and every one of them using the ratio test, but we have a rule that says when we do this, we don't have to do that. It's going to keep the same interval. All right, a quick refresher on the binomial series. I'm going to try to fit this all on here. When you do problems like 1 plus x to the p, using the binomial theorem, you learn that that turns into p things taken 0 at a time, plus p things taken 1 at a time, x, plus p things taken 2 at a time, x squared, and so on, till you get out to p things taken p at a time, x to the p. And the coefficients, p over k, we had it's p factorial over k factorial p minus k factorial was our definition for that. It was combinations. And remember that 0 factorial is 1. Okay, so we have the binomial series. It's for a Taylor series. If you're doing 1 plus x to the p, centered at 0, so it's a Maclaurin. The summation k equals 0 to infinity of p, k, x to the k. Turns out to be the summation k equals 0 infinity p minus 1, p minus 2, all the way down to p minus k plus 1, all over k factorial, x to the k, which reduces to 1 plus px plus p times p minus 1, 2 factorial, actually didn't reduce to, expands to p times p minus 1 times p minus 2, 3 factorial, x cubed, and so on. And the series converges when the absolute value of x is less than 1. And maybe the endpoints, depending on what you pick for p. So, if we go to example 4, and I'll try to fit this in here, they want us to consider the function f of x equals the square root of 1 plus x, find a binomial series for f centered at 0. Okay, so this is actually 1 plus x to the 1/2. So in our case, p is a half. Now, the very first constant is always 1. It always starts out with a 1. So we know c sub 0, meaning the first constant, is 1. C sub 1 is going to be 1/2 1, which is 1/2 over 1 factorial, which is a half. C2, not going to have enough room here, C2 is going to be 1/2 2. That's going to give us 1/2 times negative 1/2 over 2 factorial, which is negative 1/8. It's kind of weird because we never really used halves when we did combinations. And C3 is going to be 1/2 3 at a time. That's going to be 1/2 times negative 1/2 times negative 3/2 over 3 factorial, which gives us 1 over 16. So if I try to write these terms out, it's going to be 1 for the C0, and then plus 1/2 x and then minus 1/8 x squared, and then plus 1/16 x cubed, and then it's alternating, dot, dot, dot. Then it wants me to approximate in part B. This was part A, was to generate it. Approximate the square root of 1.15 to 3 decimal places. Assume the series for f converges to f on the interval of convergence. Okay, so since it's wanting 1.15 and our sequence is 1 plus x, x in this case is going to be 0.15. So all they want you to do is plug 0.15 into that, those 4 terms. So if I stick the 0.5 in, I'm going to have 1 plus, or 0.15, 1/2 times 0.15 minus 1/8 times 0.15 squared plus 1/16 times 0.15 cubed. And it says the first 4 terms gives you 1.072, rounded. So if you actually plug in the square root